Okay, so this is ASFurther notes, and we're looking at matrices, so just a wee introduction one. So first of all, just a wee bit about order. So there's 2 rows here, and there are 3 columns, so matrix P then is a 2 by 3, and the order of that then is important. For example, in matrix P, the element in the first row in the second column then is a 5. Matrices can be added or subtracted by adding and subtracting the corresponding elements. Therefore, we can only add or subtract matrices of the same order. So if we had A plus B, then in this particular case, it's going to be obviously 2, 7, 1, 4 plus 2, 1, 1, 0. Adding the 2 and the 2 gives us 4, the 7 and the 1 gives us 8, the 1 and the 1 gives us 2, and the 4 and the 0 and gives us 4. So that's part 1. Let's see if we can fit these in. B plus C should then give us 3, 5, 8, 9. And then for part 3, it's B take away A, so we'll write that one out all the way. So it's 2, 1, 1, 0, take away A, which is 2, 7, 1, 4. 2 take away 2 is of course 0, 1 take away 7, minus 6, 1 take away 1 is 0, and 0 take away 4 is minus 4. Multiplying a matrix by a scalar, or just by a regular number, then if we have A, which is 1, 2, 3, 4, 5, 2, minus 6, 7, then 4A, of course, is going to equal 4 times 1, 2, 3, 4, 5, 2, minus 6, 7. And that's going to give us 4, 8, 12, 16, 20, 8, minus 24, and 28. Minus 3A, of course, and it's going to give us minus 3, minus 6, minus 9, minus 12. I'm going to struggle to fit this in. Minus 15, minus 6, 18, and minus 21. This is straightforward then from there. Over the page. Matrix multiplication. So before carrying out, we need to make sure that they're compatible. Now, they don't necessarily need to be the same size, but the way we do our compatibility test then obviously is we write out 2 by 2 and 2 by 2, and because these numbers here are the same, then that means we can multiply the 2 matrices, and we multiply the first row by the first column. So this one here is first row first column, so that is 6 plus minus 2. Give me a second here to sort a few pages out. I'll be right with you. Yeah, so 2 times 3, which gives us 6, plus minus 2, this then gives us 4. This element here is first row second column, so we multiply the first row by the second column. 8 take away 1, which gives us 7. This is second row first column, second row times the first column, so 12 plus 10, which is 22. And then second row second column is that times that, which is 16 plus 5. We end up there with 21. Again, multiplying these two here. Not great examples actually, because they're both square matrices, but that's okay. Yeah, I have a wee bit to do in this. Hopefully I'll get it right. So first row times first column, 2 plus 8 plus 3 is 13. First row times second column, minus 1 plus 12 plus 9, which is 20. First row first column, 3, 0, minus 6, so that gives us minus 3. Second row first column, 8 and 20 and 6, which is 34. Second row second column, minus 4 plus 30 plus 18 gives us 44. Second row final column, 12, 0, minus 12, so that gives us 0. And then final row, first column, 14 and 32 and 9, which I think gives 55. Second row, second column for this element here, minus 7 plus 48, 41 and plus 27, which gives us then 68. And then final row, final column is 21 and 0 and minus 18, so we end up then with 3. Just some other definitions, and again things that we should know. The unit matrix is defined by I, and it's 1001. It's equivalent of 1 in multiplication. So if you multiply any matrix by the unit or identity matrix, then you just get the same thing. So if you multiply any matrix by this, the other way around, we just get up the original one. So your example here is 2, 5, 4, minus 1. If we multiply it through by 1001, we get 2, 5, 4, minus 1. The same with 3 by 3. For any sort of square matrix, if we multiply this by this, it's the same as multiplying the unit matrix by the matrix, which just then gives us a matrix. Singular matrix is said to be singular if its determinant is 0, so we'll do determinant I think probably in the next video. It follows that it is impossible to find the inverse of a singular matrix, as this involves dividing by 0. Null matrix, everything then is 0, and the transpose of a matrix, I guess, is nearly like a kind of reflection along that line there, if that makes sense. So the first row becomes the first column, the second row becomes the second column, and so on, and that's written then as a transpose. Determine the inverse then of a 2 by 2. This is all really just kind of revision type stuff. So the determinant, of course, is AD minus BC, and then find the determinant then of each of these. Is there no example of actually finding the inverse? I guess there isn't. But that's okay. So find the determinant of this. So determinant of A is equal to minus 9 minus 14, which is minus 23. Determinant of B, so AD minus BC, 7 minus minus 6. So 7 minus minus 6, and that's going to give us then 13. And then the determinant of C, 2x times 5x, which is of course 10x squared, take away 7x squared, and that would tidy up then to give us 3x squared.